Line P1, we're in learning task 7, which is going to be solving transformer calculations. We're actually going to break this one apart into two separate sections. We're going to go and have 7a, which is going to kind of cover the first little bit where we're going to talk about testing our transformers, percent impedances, and things like that. And then after that, we're going to go into doing a bunch of transformer calculations, banks, and things like that. So let's start with the very first drawing that they show us over here. This first drawing is a complicated drawing. I mean, it doesn't contain that many components, but it's the way that everything inside here is laid out. You know, we're not used to seeing all of these series parallel RL circuits, right? You shouldn't see any capacitance inside here. There actually is some. They just didn't go too overboard, but there should be some parasitic capacitance inside here too. But they're just showing us a bunch of different types of resistances and inductances that all together are going to go and form the total of every transformer. We're going to go and have some that are measurable, like this one over here. My primary value of resistance. I can go and measure that. We're going to have some that are going to go and show up just under operation. I'm going to have primary coil reactance in opposition to current flow that's going to be due to flux leakage. This is where I'm going to go and have fringing effects, lines of flux that are going to go around the outside of the transformer. They don't cut across the secondary side, and so therefore they're just going to be seen as an inductor. Just unused winding sections that are going to be using as an inductor. We're also going to go and have that on the secondary side. Unused winding sections that are going to be acting as an inductor. We can't capture all of our windings inside, so some of them are just going to act as inductive types loads. We're going to go and have some that are going to be calculated. This resistance that I'm going to go and have. The main resistance, our magnetic resistance, this is going to be caused by core losses. Shred losses that are going to be happening inside of our core, where we create eddy currents, where we're going to go and have a little bit of dielectric losses, where we're going to go and have some just hystereses, any of these other shred types of losses that are going to be inside of there. We are also going to go and have primary coil self-inductance. This is going to be its own opposition to current flow, which is going to go and create the counter EMF that we use to drop whatever our value is of AC that we're going to be placing across our system over here. And then, last of all, on this side over here, we're going to go and have a secondary coil resistance. This is going to be one that's going to be measurable. Now, we're not going to go into, a crazy amount of vectors and draw these things all going into every which direction. We could do that, but it's really not going to go and do a lot for us to go and do that. Just know that we've got a bunch of inductive and we have got a bunch of resistive. There can be a small amount of capacitive, but it will never be enough to counteract the overall effect. And if the overall effect is going to be RL, resistance and inductance together, well, then what do? We know that we're going to go and have a lagging type of power factor for this. All right, let's talk about the energy losses. Is there energy lost in transformer? Absolutely there is. As soon as we feel heat, right? We've got heats that are going to come off of this thing. We know that that is going to be energy that is not being transferred out to wherever my load is going to go and be, right? So we do have to go and measure those losses. Now, we're going to have two main types of losses. We're going to have core losses, and we are going to go and have copper losses. We do need to add a little bit onto what they have stated. They talk about core losses, that they're going to be eddy currents, circulating currents inside of the iron, and hystereses, how hard it is for us to twist those domains back and forth that are going to cause those. We are also going to have another one called our dielectric loss. And the dielectric loss is simply going to be the loss that is going to go and happen inside of the insulation around our conductors, right? The orbitals of that insulation around our conductor. So this center part here is the conductor, but the orbitals around here are going to be changing back and forth because I'm going to go and have a AC current that's going through here. So there's going to be a tiny amount of heat given off of that. If you bend plastic back and forth, it will generate heat. We're doing at a molecular level, or atomic level, we're doing a bending back and forth of our plastics. So we will get a little bit of heat off of that. Add dielectric to your core losses. Copper losses are going to be I squared R. In other words, the amount of current that I'm going to go and dump through here, that amps, we're going to square that, multiply that by the resistance. It's going to go and give me copper losses. I'm going to have I squared R that are going to be through here. I'm also going to go and have I squared R that are going to be through here. Two main ways that we can go and test. We can measure our core losses through an open circuit test. It's not a complete circuit, so we're only able to measure magnetizing current and magnetizing losses. So that will be my core. Copper losses are going to be done through a short circuit test. Now, this isn't a applied short circuit. This is a Very, very specific methodology that we are going to go and apply a short circuit for it. Let's start with the one where we are going to look for our core losses. Note that my transformer is isolated on one side. We don't have a short circuit. We're going to feed power in onto one side. That side will become what we refer to as a primary. And then we are going to go and take absolutely no current out the secondary. In other words, the only things that this should be supplying is going to be any magnetic losses that are going to be happening inside of here. So what we're going to do is we're going to start by taking our high voltage leads. We're going to go and isolate them. They can't be connected to anything. We're going to cap them off, stick some barrettes onto those things. If it's like 600 volts up, and stick a bit of tape around, hold them on there. We're going to make sure that they are isolated somehow. Then what we are going to go and do is we're going to apply full rated voltage. Let's say that this transformer over here is rated for 600, 120. This would be 120 then that we would go and apply to this over here. What I'm going to go and do is I'm going to go and measure what's going on inside there. Now they show us having a voltmeter across here. We're going to use that to measure. If we're applying the full 120 to it, we're applying the full 120 to it. This is just for verification there. You apply the full 120, you should see that full 120 that's going to be across here. Once again, our ammeter, for those of you that don't remember how ammeters themselves are connected, what our wattmeter is going to do is it is going to have a current section, it's got an ammeter, that is going to be tied to a voltage section inside of here. So these two are going to be tied together, and they're only going to go and display true actual watts. They only display anything that's going to be an in-phase type of current. This volts, this amps over here, I can multiply those two together because they're separate, and I would be able to get a VA off of these two. But this wattmeter measures both current and voltage at the same time, and when it does that, it goes and only measures it as true watts. So what I'm going to do is I'm going to now apply that full rated low voltage to this. Once I take this voltmeter out, so it's not loading, if it's a good voltmeter, it shouldn't make much of a difference because it's going to have an extremely high value of resistance. But what I can do is I can go and read now what amount of power I'm taking off of here. The only power that is going into this circuit would be anything that would be dissipated as true real heat, because we got no load connected on this side over here. The current that is going to be flowing inside of here is also going to be really, really small, right? We don't have a lot of current that's going to be needed to go and create those little tiny bits of watts that we're going to take off it. We're not transforming any current through here, so we've only got what we refer to as our magnetizing current. Should be low, it's going to be well less than 10%. Anywhere from like 1 to about 7-ish seems to be fairly common on the ones that I've tested. But it's never going to be, up to like 10% or something like that. It's going to stay relatively low. It's going to be small amounts of heat that are going to be caused by my eddy currents, as well as my dielectric losses, as well as my hysteresis losses over there. Literally, we just read it off of the wattmeter. Super easy test. The other one's a little bit more complicated, the short circuit test. And the short circuit test is going to be us applying a variable AC source. Now, there's not a lot of variable AC sources out there. Most of you do not have one at your place of work. In fact, most of you are probably never going to do any of these transformer tests because usually everything that's going to be discovered in these tests will be written on the nameplate. However, if you do work for, heavy industry where stuff needs to be done right and done proper, and you need to do some of your own testing on site, or you have old pieces of equipment that are going to be refurbished or put back into service, or you're tracking down problems, you might end up doing this stuff. Over time, transformer ones do this process called degassing, where the VOCs, the volatile organic compounds, start to go and evaporate out of the varnish that's going to be applied as my insulation. And as that happens, my resistance is going to go and change of that insulation. I start to have more leakage and things like that. And so what I start to get is a change in my transformer's output. So we periodically have to take some of these transformers out of service and test them. And you're going to go and see differing values that are going to happen for your core losses and your copper losses as a transformer will age. It's just, stuff is wearing out, right? All right, so let's go and start with this one over here. This is going to go and follow a couple of steps very similar to the other one. We are going to go and use, once again, a wattmeter. That's going to have the ammeter section and the voltmeter section inside of it. We are also going to go and take our transformer and we're going to short circuit one side of it. We're going to go and short circuit the low voltage side of it together. The high voltage side, we're not going to feed it with the high voltage. You know, if this is that same 600 volt transformer that we had, 600 to 120 volt transformer, we're not going to be feeding 600 volts in. Instead, we're going to be feeding in a very low value of voltage off of a variable AC source. You know, this might be like a 24 volt AC source that we're going to be feeding into. It's going to have to be the proper frequency. It cannot be a variable DC source. It has to be an AC operating at the same frequency as the load itself is going to go and be. What we are going to do is we are going to basically just ramp up this thing until we hit the rated amps. So we're going to start by ramping it up. Once we hit our rated amperes, then we are going to go and read the volts. I'm going to write that down because we're going to need that. And then we are going to go and read the watts after that. It's a fairly simple test, really, when you take a look at it. So I make this connection. I start out at 0, and I'm going to start ramping this thing up. And what I'm going to be doing is I'm going to be watching until I hit my rated amount of amps inside of here. So this might be rated for, I don't know, let's go and say that this one is rated for 20.8 amps. What I'm going to be doing is I'm going to be watching this thing. As I'm turning the dial on my variable AC source, I'm watching this thing until I hit 20.8 amps. Once I hit 20.8 amps, I'm then going to go and stop adjusting this thing. I'm going to mark down that value of voltage. That's going to be referred to as my impedance voltage, my VZ that I'm going to go and have over there. Impedance voltage is going to go and be critical to us later on, so we do want to have this thing marked down. Once I've got that VZ, and we're measuring that VZ right over here, because it needs to be across the transformer, not across this side over here. But once I've got this thing at the proper current, I measure that voltage, record that VZ, and then I'm going to go and remove the voltmeter from the circuit so that my wattmeter is not reading any of it. Then I'm just going to measure with my wattmeter. I'm going to take the reading off of it, and that's going to go and tell me what the full load copper losses are. If I've got full current in the primary side, I've also got full current in the secondary side. You know, whatever my secondary might be, it's going to be some multiple of it. This one's going to be, you know, like 104 amps, I think it would work out to be, something like that. But it would be reading, it would be running through here, therefore it would be dropping the full I squared R on the secondary side here as well. The impedance voltage that we are going to go and have is only going to be a small percentage of what the rated is going to go and be. So if this was a 600 volt one, we're going to be somewhere down, you know, like maybe 2 to 5, somewhere in that range, which means that what I should expect for a 600 volt one like this is somewhere like maybe 15 to 30-ish volts. That is going to be my full impedance over here. What I'm then able to do is I'm able to take all of this and use this to go and make some calculations. Now, we've talked about transformer efficiency. We know that transformer efficiency is going to be a measure of my power out over top of my power in. And we know that power in is simply going to be power out plus losses. What type of losses do we have? Copper losses, and we have got core losses that we are going to go and have. If you go into your binder, they do show a really long fancy formula where it shows E times I times cos theta. In other words, this amperage and a voltage, you know, multiplied by cos theta, which is really just a conversion of VA into watts, right? It's power. That's all that they're doing. Everywhere that you see E times I times cos theta, you can just bracket E times I times cos theta. You can bracket that off and substitute in watts. It's just a fancy way of writing watts that for some reason somebody decided was a good way to put this into here. It should just be, you know, load watts plus copper losses plus core losses. That's what the bottom part of that formula is. Don't get tripped out, you know, by this thing. I know sometimes they've got, you know, far too much math inside of this one than what you need to be able to do. You need to be able to describe. Remember, that's the primary thing that we had to do throughout here is describe. You need to understand what's going on inside there, not, you know, show off some fancy formulas. Over here, in the next one underneath there, they talk about a transformer that's tested, and it has core loss of 1200 watts, and then copper loss of 1627 and 1562, and then the secondary is delivering its full rate 250 kVA at unity power factor. What is the efficiency of that transformer? They're just doing the same thing over here. They're going to go and take the watts. It's 100% power factor, therefore 250 kVA is 250 kilowatts. And then they're just going to add in the other watts. I do want to point out as well that you're not going to know your copper losses difference from the primary to the secondary, right? How many places do we measure? We only measure one place. We only get one wattage reading. That wattage reading is going to be this copper losses plus this copper losses that we are going to go and have over here. Now, let's talk about this percent impedance thing, because this is going to be really critical to us. We don't do a lot of transformer testing the way that we've just been shown these ones in most day-to-day operation for most people's application. However, we do a lot of installations, and installations are all going to be based upon a percent impedance, because we need to have interrupting capacity of our devices, right? We can't just go and place something in there and then have no way to go and shut it off underneath the fault. So we're going to have percent impedances. We use it to calculate the available fault current. That's the maximum amount of current that could flow underneath a fault, as well as we use it to determine whether we can parallel two transformers, right? We talked about a percent impedance. Percent impedance just talks about the resistance of a transformer. And if we've got unequal percent impedances, we're going to have unequal voltage drops, and therefore we could not go and parallel those things. What they do then is they go through a little bit of math once again. If you go into your binder over there, they show that they talked about the percent impedance voltage, or IZ, because IZ is the same as V, right? V is equal to I times R. What we determined off of this was we determined our impedance voltage. Remember that? We said the VZ that we had. Now they're taking the V, and they are going to go and expand the V into I and R, current and resistance. What's my resistance? Well, it's going to be an impedance. So they call this thing, instead of having the impedance voltage, they call it the percent IZ. And then what they're going to do is they're going to go and divide out current out of this thing to go and show that whatever my percent voltage is, my percent V, is going to be the same as my percent Z that I'm going to go and have. In other words, what I measured out of here, let's say that I measured 20 volts as my voltage at my impedance over here, right? We did that VZ. I measured 20 volts. This thing was a 600 volt rated transformer. All I would have to do is go and say 20 divided by 600, and that is going to go and tell me that this transformer has got a 3.3333% impedance. This is really critical to us, because once we got this percent impedance, what we're able to do is we can determine the maximum amount of current that would go and flow underneath a fault. Let's take the same transformer, since we have worked with it so far. We're going to go and give it some values. We're going to say this is a 600 to 120, because that was what we worked with, 600 to 120. And let's give this thing a kVA. Okay, we're going to go and call this thing a 20 kVA. Which means that if it's 20 kVA, I've got 20 kVA on the 600 side, I've got 20 kVA on the 120 side. What is the maximum amount of current that could go and flow through either one of those? Well, we can just take 20,000 divided by the voltages. So we'll just do that. 20 divided by 600 gets me to a value of 33 amps that I could have on the primary side. I'm just going to draw this out over here if I'm feeding in on a high voltage side. So this thing could be rated for 600 volts, 33 amps at its maximum, right? It's not going to carry that unless the load is demanding that. And then on my secondary side, it's going to be the same kVA, 20 kVA divided by 120. Which gets me to a value of 166 amps that I'm going to go and have. Round that to 167 amps, and that's going to be at 120 volts over there. Okay, so we can connect load. We can draw out up to 167 amps. What we need to do with this percent impedance is the percent impedance is always going to go and help us select what we have in our primary circuit over here. Worst case scenario that could happen would be that some idiot out there goes and bolts across the bottom of our transformer. Hey, look at this. I created a short circuit. You drop a wrench across a bus bar or something like that. As soon as that happens, how many amps are going to flow in here? A ton. What's the only thing that's going to be opposing the flow of current inside of there? The impedance of the transformer itself. Which means that impedance of the transformer itself is going to go and throttle back the current, but hardly. So we're going to get a mass amount of current that's going to flow through here, which would mean that we're also going to go and get a mass amount of current that's going to flow through here. Remember that when my secondary current rises, my primary current rises, but it's just a smaller reflection of it. How many amps should we normally have inside of this primary? 333 amps. So what is my maximum available fault current that is going to go and flow on this side and on this side underneath load? All we need to do is we need to take these amps and divide it by our percent impedance. On this side over here, the maximum current that's going to be flowing is going to be my full load current, 167 amps, divided by 0.033. Our 3.33%. We take our full load current, and they give you the formula over there. ISC is equal to I rated, full, they call it inside there, divided by percent Z. You need to have this. You're going to use this inside of protection, circuit protection. You're going to use this inside of motor control. You're going to use this inside of third year. You're going to use this in fourth year, and you will probably use this on your IP. You need to know your rated current divided by your percent impedance is going to give you the fault current. What is the fault current? Let's try these both out. 166.67, so that's my full current, divided by 0.033. Gets me to a value of, on the secondary, I'm going to have up to 5,000 amps. That's going to go and flow. 50 amps, short circuit, SC that we're going to place. On the primary is also going to go and see the same rated rise. So I'm going to have 33 amps over here, divided by 0.033. Gets me to a value of 333 divided by, gets me to a value of 1,000 that I am going to go and have. So I'm going to go and have up to 1,000 amps that I'm going to have flowing inside of this 600 volt circuit. This 600 volt circuit, on our primary side, we need to have a disconnect. We sometimes have got fuses and circuit breakers on the primary side and on the secondary side. But if I would have a primary circuit breaker, it would have to be rated to carry this. So we're going to use a 40 amp breaker to carry the 33 amps. But then it's going to have to be rated that it can open up to 1,000 amps of fault current. On this side over here, I'm going to be using a 200 amp breaker for this 167 amps over here. But I'm going to be making sure that that thing is going to be rated to go and open up underneath 5,000 amps. This is where you're going to go and have interrupting ratings on your breakers. Breakers and fuses are always going to go and have their rated and then their interrupted rating. If you go and take a look at a circuit breaker, standard circuit breaker, it's going to go and be rated as 50 amps, but then if you read the fine print on there, a lot of them are going to go and say that they're going to have up to 10,000 amps interrupting capacity or interrupting rating. That's the short circuit rating. That's why we need to be able to calculate this, because if I would have a short circuit current that would be greater than the interrupting capacity, that thing won't be able to do it. Can't hack it. Can't do it. If I end up with a 30 kiloamp short circuit current, I cannot interrupt that with something that's got a 10 kiloamp interrupting rating. They give you another example inside of there where they're going to go and give you a 100 kVA transformer that is going down to 120 volts on the secondary side, which is 833 amps rated current. And then they go and say, what's the percent impedance? And they take that 833 divided by that 3% impedance, and they end up at close to 30,000 amps. It's 27 kiloamps that we have that thing could go and put out. You would once again need to make sure that you can interrupt that rating. All right, we are going to stop right here. We're going to do the next set of calculations as a separate video.